All right, if you'd please calculate these for me. Here's theta in degrees. Here's theta in radians. Here's the sine of theta. Theta in degrees, in radians. Okay, so first, let's do this together. Here's 0 degrees. How do we get from degrees to radians? Do we remember?
Yes.
How many people need just a quick?
I have the units.
So remember, one circle, you better pen.
You divide by 360 and multiply by 2
One circle equals 360 degrees equals 2 pi radians. Do we agree with what I just wrote?
Yes.
So now, you can either put 360 degrees over 2 pi, or you can put 2 pi radians over 360 degrees. And yes, I know there are people out there saying, or you could just do it with pi radians. It's the same thing. This is the way I remember it, because a full circle is 2 pi radians, a full circle is 360 degrees. Always use whatever is easiest to remember in the long term, not the short term, because you want to keep this information as long as possible. So take this, and obviously it's going to give me
0
0,
radians.
and then sine of 0 is?
That's 0.
So now we're going to go 5 degrees, and I want this as a decimal, not as a fraction. I know, fractions are better.
Dude, who does not like a good fraction?
Shut up, Jackson.
I can't graph pi over 6 on a graph. I know math loves it, but it doesn't help.
You can if you do.
No,
can
I
if
do
your
not
scale
want
is
to
in
turn
pi
to
over
pi.
6.
Is 0.1 something?
Exactly.
0.0873.
0.08, what, say again?
0.0873.
Okay, put it in here. Sine of that, it gives me,
0.087.
is it the same?
Yeah, it's like 0.0872.
All right, so now 10 degrees, give me that in radians.
.175.
0.175.
3.
3. Take the sine of that in radians.
So if you want it to the fourth decimal, on 1745.
Is this 1745?
It's
You're good.
0.1744.
0.1744. Okay, now 15 degrees. You guys agree on those numbers?
0.261.
What is it?
0.2618.
1.8. Now take the sine of it.
0.26 or 0.2588.
Oh, it's diverging a bit, isn't it? Now I want 20 degrees.
0.349.
349. And over here, 0.342. Notice? You notice it's diverging more, isn't it? This is known as the small angle approximation. In less than 15 degrees, we say that the sine in radians is equal to that degree in radians. There's another one, yeah, that you'll work on if you ever get to optics, where if you take a large, I'm running out of ink here. You take a large, an angle that undergoes very small displacement here, very small angular displacement. If this is your hypotenuse, this is adjacent, and this is your opposite. Well, wouldn't these two be basically the same?
Yeah.
And so in that case, the sine of theta is roughly equal to the tangent of theta when they're very small. That happens in diffraction all the time. Okay, so now that we have this small angle approximation, there we go. That's our small angle approximation. Let's talk about pendulums now. We're gonna have to do a bunch of little kind of funky things here, but it'll work out pretty well. Let's say we have a pendulum. We've got our mass down here. Just take a spot here. Call that L. And let's call this the arc length, S. Arc length. wish I had a pen that was writing a little bit better right now, but they're all kind of petering out on me here. See if this right one's pretty good. Okay, so now we have our arc length L, and we'll call this theta. Well, let's do a force diagram on it. We know we have mg, we have a tension going this direction, and then we have a force tangent to its path trying to pull it backwards. Well, is that sine or cosine? Would you agree that this right here is the horizontal?
Yes.
Would you agree as this falls, that as theta, way up here, as theta gets smaller, this becomes horizontal?
Yes.
So therefore, if this is theta,
That's-
this is also theta.
Yeah.
So this force right here, my restoring force. So here we go. My restoring force is mg sine theta. Would you agree that it's only equal to mg if the pendulum was all the way up here? When it's all the way at the bottom, there's nothing pulling it to the center, so there's no restoring force at all? There's a force mg, but it's balanced by t, and there's nothing pointing to the center. As you pull it farther and farther away, it pulls more towards the center. Okay? Obviously, the m's cancel. You know when we found out a pendulum that didn't matter the mass?
We sure did.
Interesting.
Sure did. Sure did.
Now's where we're gonna have to get a little bit strange here.
Wait, no.
It's fine, guys, there's nothing.
So now let's look over here. Arc length. Our arc length is defined as what? Radius times angle, which will be L theta in this case. Do we agree with that? Yes? And here's where we're gonna have to do some approximating, okay? Would you agree that this is rough, very, very small? That this distance right here is roughly x, and those two are very close to one another in length?
Very good. Sure.
So then we could say that x is approximately equal to s, which equals L theta, doesn't it? And so that we can solve for theta, which would equal x over L. Yes? And if it's a small angle, we know that the sine of theta is basically equal to theta.
Yeah.
So we can plug in g x over L. Oh, I made a big mistake here. That's pushing backwards, but I have that. Equals my acceleration. I'm gonna pretty it up just a little. Negative g over L
Dang.
times x equals the second derivative with respect to x. And that right there has to be omega squared.
Dang.
I have to write this down. Can we see that right there?
Yes.
So we found out that d squared x over dt squared equals negative omega squared x. That's what we found earlier. So now, we put this all together and we get omega squared, which equals g over L. And that equals, take the square root, so omega equals the square root of g over L, which equals 2 pi over t, and t equals 2 pi square root of L over g. Yeah.
So does this mean that pendulums are only in harmonic motion when they're in a small angle?
They're actually simple harmonic motion for small angles. As you get larger angles, they get farther and farther from simple harmonic motion.
Because then they